I'm going to speak about dual Grothendieck polynomials and Danilov-Koshevoy arrays. This is something we started with my former student Anastasia Sukhachova. And the talk will be mostly about combinatorics. And well, there will be some geometric motivations. And since there are many specialists in representation theory in the audience, are addressed to you guys. Please tell me if you see something familiar from representation theory, because so far I'm sure that the objects which will occur in my talk must have some representation theoretic meaning, but I don't know any for the moment. So, okay, so let's begin. And here's the outline of my talk. First, I'll recall from the combinatorial point of view what are Schur polynomials. And then, so my talk is aimed, well, to graduate students. I see some in the audience. So, Lena, I'm not sure it will be aimed to the youngest one. But, okay. So then I'll talk about, well, this is a very classical object we saw in today's first talk by Nadia. And then I'm going to speak about dual Grothendieck polynomials, which I will define also combinatorially and say something about their geometric meaning. And then I will present a combinatorial means of, another interpretation of things related to Schur polynomials, Young tableaux, and so on and so on. Danilov-Koshevoy arrays from their paper of 2005, which I believe got much less attention than it deserved. And then I'm going to talk about the generalization of these arrays, which something we call arrays with strings, which is basically rhymes with two, well, something to deal with dual Grothendieck polynomials. So, is there going to be any connection to Horn conjecture? Not that I know of, but I don't know. I was so probably everything is related to Horn conjecture in this business. No, it's another one. Yeah. So, well, first let me define Schur polynomials. I'm going to start with a partition, which is for me the same as a Young diagram. So rows are left adjusted and start from top to bottom, weakly decreasing. So this is a partition 6632. And each time I have a Young diagram, well, I have an intention to fill it boxes with something. So let me define a Young tableau. A Young tableau is a way to fill these boxes by integers from 1 to n. N is some fixed natural number, which will be the number of variables in my Schur polynomial. And I want my filling to be row semi-strict, which means that along the rows, the entries weakly increase, and column strict. That means that in each column, the numbers increase strictly. And so this is a semi-standard Young tableau, just Young tableau for me. And each time I have such a tableau, I can assign to it a monomial. That means for each entry, xi, let me take the corresponding variable x. For each entry I take the corresponding variable xi, and I just multiply everything, all the x's I got in for this tableau. So in this example, I've got like 2 1s, 3 2s, and so on. 1 6 and 1 7. So here's the monomial, and the degree of this monomial is equal to the number of boxes. And what I do next, well, I'm saying that this Young tableau has shape lambda. So lambda is the underlying diagram, and I can take let me take some smaller example. So let me take the diagram 2 1 and n equal to 3. So here I have all the Young tableaus filled by 1, 2, and 3. So there are 8 of them. and I can sum these monomials up, and what I get is called the Schur polynomial. And you see here that, well, a miracle happens. This polynomial is symmetric in 1, 2, and 3, and from the definition, this is absolutely not obvious. From this combinatorial definition, this is, well, there's no reason why 1 should occur as many times as 3. Not there. But okay, so that's some questions, some problem I sometimes ask students who want to study this. Well, just to show that polynomial defined in this way is symmetric. So if you solve this exercise, what you will get most likely you will construct some. Well, if you're solving this exercise, most likely you would want to construct a bijection on these tableaux, bringing I to I plus 1, something like that. And if you do this, this will be called the Bender-Knuth involution on the tableaux, something which has a nice interpretation also in terms of arrays, which I'm going to discuss a little bit later. So yeah, so these polynomials are symmetric. They form a very nice basis and the ring of symmetric polynomials, and they occur in many places. Like first of all, and most important thing is that these are characters of representations of GLN, and so yeah, their symmetry follows from Weil's character formula, and then if you like algebraic geometry, you can say that these guys represent Schubert classes of in the cohomology ring of a Grassmannian, and then well, they have many nice combinatorial properties. Namely, if, well, I mentioned that they form a basis. If you multiply 2 elements in this basis and expand it with respect to polynomials, you'll get some coefficients here. They will be integer and non-negative. And of course, if something is non-negative and a negative integer, you would like to know the combinatorial meaning of this number. Well, so in this setting, this will be some number of points in intersection of certain Schubert varieties. And in this setting, this will be some multiplicity of an irreducible representation in V nu in the tensor product of B lambda V nu. And well, if you want to do combinatorics, you need to deal with some skew Young tableaux with certain combinatorial, with certain extra conditions. And well, yeah, so you can get a description of these entries in purely combinatorial terms as well. Okay, so let me just generalize this setting. Let me relax a condition of column strictness of Young tableaux, and let me consider Young tableaux which are column semi-strict. This means that these numbers in columns increase, but weakly. They're allowed to be equal. Like here you have 1, 1, 1, and here you have 2, 2 in the third column. And well, you can play the same game. So why don't people play the same game? Well, so well, this will be called a reverse plane partition. All right, the plane partition is something row weakly decreasing and column weakly decreasing, and this is other way around. And well, if you assign monomial to such a thing and you sum all these monomials over all reverse plane partitions of a given shape, bad news is that this won't be symmetric. So there must be some other way to assign a monomial to this thing. And here it is. So instead of multiplying xi's for all entries in in the boxes, you take xi as many times as the number of columns this entry appears in. So, for instance, here in this picture, one is contained in two different columns, the first and the second ones. So you take x1 to the power 2 instead of the power 4. 2 occurs in 3 columns, x3 in 2, and x4 only in the last column. So the monomial you're going to get is this, and obviously it has its degree is smaller than the degree of what you expected to get at the beginning. Well, it will be only equal in the case when diagram and the tableau is column strict. So this rule works in the same way both for reverse plane partitions and semi-standard Young tableaus. And you can sum these monomials, and what you're going to get will be called the dual Grothendieck polynomial. I'll tell you in a couple of minutes why it is dual, and sometimes it's also called dual stable Grothendieck polynomial. And I don't want to explain what stable means in this thing. So these were defined by Thomas Lang and Pasha Pilavsky in 2007, and these polynomials are symmetric, as opposed to what you would get according to the first rule, which is marked as wrong here. And obviously, since all semi-standard Young tableaus are also reverse plane partitions, well, you'll get S lambda plus some terms of lower degree, which come from column weakly increasing tableaus. Okay, so let me tell you briefly about some geometry. Yes, in particular, yeah, good remark that it is obtained by a triangular change from the basis of Schur polynomials. So this is again a basis. You can view it as certain deformation of the basis of homogeneous Schur polynomials. These guys are not homogeneous. So to Schur polynomials, you add some lower degree terms, and this, of course, is still basis. Yeah, and well, here's some geometry which is behind it, and so if you take a Grassmannian, you can take its cellular decomposition into Schubert cells, and their closures are called Schubert varieties. They are interesting from various points of view, and well, you can take their classes sigma lambda in the cohomology ring of a Grassmannian, and they can be identified with Schur polynomials, well, such that the partition lambda fits into a certain box. So basically, you have a map, a surjective map from the symmetric functions to this ring, and Schur polynomials are mapped into Schubert classes. Okay, so if you want to do intersection theory, well, this is reduced to a purely algebraic problem. Okay, and then another setting will be considering the K-theory of a Grassmannian instead of the homology ring. So you can speak about coherent sheaves on the Grassmannian, and you can take the structure sheaves of Schubert varieties, and also you can take the ideal sheaves of Schubert varieties, and you have an exact triple like this for each Schubert variety. So the ideal sheaf is mapped into regular functions on the whole thing, and if you mod this out by the ideal, you get the regular function on the Schubert variety X lambda. And you can take the classes of these guys and these guys in the K group, and it turns out that the classes of the ideal sheaves are represented by the dual Grothendieck polynomials. And as you can guess, the classes of the O of x lambda are represented by what is called Grothendieck polynomials. That's why these guys are called dual. And if, well, algebraically, if you take the inner product on the whole inner product on the set of symmetric functions, which, well, according to this product, the Schur polynomials form an orthonormal basis. These two bases will be dual to each other. Well, in particular, this guy, G lambda, is the corresponding Schur polynomial plus some higher terms. So, well, that's how it works, and that's the geometric motivation for considering dual Grothendieck polynomials and Grothendieck polynomials as well. These guys, well, I was not planning to speak about them today, but they have a also very nice description in terms of so-called set value tableaux. So in the boxes, you can put not just individual numbers, but subsets of numbers, and take a monomial of possibly higher degree, which corresponds to a tableau, sum them up. This will be called, this will be the Grothendieck polynomial. Okay, so let me tell you something more about Grothendieck polynomials. Well, as we know, since they're symmetric, they can be expressed in the Schur basis. And it turns out that these coefficients of expression of G lambda in Schur basis are non-negative. So we know about one coefficient. It is 1. So G lambda is S lambda plus something of smaller degree. Well, and it would be interesting to get an interpretation of these coefficients F lambda mu. And it turns out that, well, they have a combinatorial meaning. This is the number of the so-called elegant skew tableaux of shape lambda slash mu. And, well, shape lambda slash mu means that these are, well, you fill the boxes of the diagram lambda minus the diagram mu. According to the standard rule, it must be row weakly increasing and column strictly increasing. And here comes an extra requirement, which makes them elegant. The entries in the ith row do not exceed I minus 1. In particular, what about the first row? There must be no entries in the first row. This means that the diagram mu, the first row of the diagram mu should coincide with the first row of the diagram lambda. Okay, so let me give you an example. So consider the diagram 2, 2, 1, and let us draw all the elegant skew tableaux of shape lambda slash mu, where mu is some subdiagram of this fellow here. So first of all, you can take mu equal to lambda itself, and there's no filling, so, well, this is an elegant tableau. Then you can take a 2 by 2 square and fill the remaining box by 1 or 2, right? Because the number in the third row should not exceed 2 according to this rule. And then, well, you can take other shapes, for instance, this one, and in this remaining box, the entry should be equal to 1 because, well, this is what prescribed by this rule. And there are 2 tableaux of shape 2, 2, 1 minus 2, 1. So here they are, 1 in this box and 1 or 2 in this box. And the last one is just 2 with a unique elegant tableau of this shape. So what you get in this case is such an expansion of the dual Grothendieck polynomial in terms of Schur polynomials, right? Okay. And well, yes, this is what I wanted to say about dual Grothendieck polynomials. And Let me switch to the third topic I was going to speak about today. These are Danilov-Koshevoy arrays. Well, Grothendieck polynomials are sure. Well, the sign is interchangeable. Well, it's like well, the usual Grothendieck polynomials are as lambda plus well, minus something of degree lambda plus 1 plus something of degree lambda plus 2. So if you change xi into negative xi, they become oh well, either positive or negative depending on their degree. So yes, and well, it's pretty easy. Okay, let me tell you about the arrays. An array is just a matrix with non-negative integer entries, which is usually written according to Danilov and Koshevoy in a slightly unusual way. You just number the entries as they define in the first quarter. So like 1, 2, 3, 5, and 1, 2, 3, 5 go up, not down as it is the usual case with matrix. So the entries are interpreted as the number of some small objects, some balls and marbles, which you put on a chessboard. And here's an array, and well, you can say, well, you can think about it as about a bounded thing, or maybe infinite with finite number of non-negative entries, as you wish. Okay, so and I'm going to play a game. I'm going to move these balls around according to certain combinatorial rules. So I'm thinking about the entries as not just integer numbers, but number of some objects. Okay, and I'll define 4 kinds of operations. The horizontal ones, dj and uj, which will move at most one ball down or up. From the row dj moves a ball from, well, at most one ball from the row j plus 1 to row j. So they are local in this sense. They affect only 2 neighboring rows. And well, uj will do the opposite. And li and ri will do the same with columns. So the rule to define which ball is being moved is quite complicated. So let me tell you now how to determine this. Well, suppose I have 2 rows and I want to drop one ball from this row from the top row to the bottom row. So what I do now is I construct something called stable matching between the balls in this row and this row. How do I construct this match? In the beginning, I say that all balls in both rows are free. And then I'll pair some balls in this row with, I'll find some partners for them in the row downstairs. So the rule is as follows. I read the top row from left to right, and I'm assigning to each ball the rightmost ball in the bottom row strictly to the left of it. So all my so in particular, and well, if there is no possible partner to be paired with, this ball is remained free. Well, so these guys in this in this box are free because there are no balls strictly to the left, right? Well, there's no one in this box, so I'm switching to this one. So I'll say that the rightmost free ball in this row lives in this cell, and the rightmost free ball partner for this guy lives here, right? Okay, and when I switch to this box now, I'm saying that one of them will be paired with the remaining free guy in this cell because there are 3 of them and 2 of them are taken by those 2, right? And so there is a partner for this fellow here, and then these 2 guys get partners in this box because everyone in this box is matched. Okay, and this fellow here remains free. Okay, and for the last 2 of them, their partners are just in the neighboring. Okay, so after I have constructed such a matching, let me take the rightmost free ball in the top row and drop it down. So in this case, well, this is the rightmost free ball, and it goes. Okay, well, so this is the result of the operation BG, and sometimes this ball may not exist. So if all the balls are in the top row are matched with someone downstairs, this means that my operation just acts trivially. dj a will be equal to a, so it doesn't change the average. And well, suppose I dropped something down. An easy exercise is to show that if we now construct the matching between these 2 rows with this guy who went downstairs, this fellow here will be the leftmost free ball for this new match. Well, of course, it will remain free because all the guys to the left of him have someone to be paired with. Okay, so that's what uj does. It takes the leftmost free ball in the bottom row and lifts it. Okay, and in this case, you see that, well, if an operation dj is efficient, which means that if it changes the array, the corresponding uj is the left inverse of it. Okay, so they just they act like generators of the symmetric group, but not quite. Of course, there is far commutativity, but if you want to write a braid relation, you need to change. You need to take not an individual dj, but some maximal power. Okay, and so I can also define left and right operations, act on columns. So just to be quick, I'll say that AT will stand for A transpose with respect to the main diagonal, and LI is just DI A transpose. Same about R. And well, it may happen that all the all the downward operations are non-efficient. In this case, an array is called dense. And then, well, if you have some certain array, not necessarily dense, you can consider its condensation, which means you apply downward operations as long as you can. So, and here's a result that, well, this decondensation does not depend upon the order of the downward operations. So if we take the same array, and I will condensate it in applying some sequence of operations, and you will do the same with some another sequence of operations. At the end of the day, we'll get the same thing. Okay, and one more funny thing which I didn't put on the slide is that the left of the horizontal operations commute with the vertical ones. So each dj commutes with li and so on. Okay, so let me just play with d-dense arrays. So here you see an array, and well, you could believe me or just check by yourself that this array is d-dense. So let me read it in the following way. I read it row by row, from the left to the right, from bottom to top. And I read it in the following way. I look at all the balls one by one, and I write the number of the column this ball is located in. So here I'll read 1, 1, 1, and 1. So I have 4 ones. So here I'll say 2 and 2, and I write 2 2s in this row and 4. There's no one in the third box. So if I read it in such a way, I'll get something which looks like a tableau. So the thing is that if the result, well, so the second, I read the second row 2 2 2 3 3, and the third row 3 4 4. The result is a tableau if and only if this array is d-dense. So it's what when this is semi-standard. Semi-standard, well, yeah. Mm-hmm. Okay, and yeah, so d-dense arrays are in biject correspondence with semi-standard Young tableaus. And what's their shape? To get the shape, you need to condensate it to the left, or just take the number of balls in rows. So in this row you had 7 balls, and these 5, and here 3. So here's 7 5 3, and you'll get the same if you just condensate this d-dense array to the left. So well, and another easy observation is that a d-dense array is necessarily lower triangular. The balls above the diagonal are empty. The boxes above the diagonal are empty. Why is it so? Because, well, there must be no one in this column, because otherwise they would not be free in all the columns, in all the rows except the bottom one. Well, for the second column, there must be no one in this row, because the guys in this box might be only paired with guys in this box, and this box is empty. So this box is empty as well. So an d-dense array is lower triangular, and L-dense array is upper triangular. Right? So an array which is dense both in leftward and downward directions, a bidense array, is something which has non-zero entries only on the diagonal, and it is easy to see that these entries are weakly decreasing. So bidense array is the same thing as a Young diagram, right? Okay. So far so good. And here's the main theorem by Danilov and Koshevoy. It is as follows. If you have an array A, you can take it to you can take its downward condensation dA, or leftward condensation L, and they well, and if you apply the condensation in a different direction, you'll get the same thing, since these operations commute, as I mentioned. So a theorem says that the set of arrays is the fiber product of D and L over B. This means that if you take an array, you can take its images here and here, which condensate to the same thing. And this is a bijection. That's the theorem. That is, if you take a downward D-dense array and L-dense array, which condensate to the same bidense thing, there must be a unique array somewhere upstairs, such that this fellow is the D condensation of dA, and LA is the L condensation. Okay, so, and that's a really easy but very powerful. Well, there is something to check there. I'm not saying it's easy, but it's really powerful. Because, well, let me just show one example, which I believe familiar to most of you. This is the RSK correspondence. So let me take the permutation array. Let me take a square chessboard, and let me put balls in such a way that there is exactly one ball in each row and one ball in each column. So, in other words, this is a permutation. A permutation gives me some, well, if I just take this permutation matrix, if I condensate it downwards, what am I going to get? Well, the reading tableau will be standard. This means that each entry occurs only once, because, well, if I condensate something, still I will have exactly one ball in each column. Because when I condensate something downwards, balls only move up and only move down. Right? So this will be a standard tableau. And L is a standard tableau as well. And they have the same shape. Right? So what I get is that Sn is, well, that permutations are in a bijection of, with pairs of standard Young tableaus of this age. And in the language of representation theory of finite groups, this is just the Burnside formula for Sn, because, well, the dimension of an irreducible representation of given by a partition lambda is just the number of standard Young tableaus, the Koska number of k lambda, and the n factorial, the order of the symmetric group, is just the sum of k lambda squared over all partitions. So, like,
sorry.
Yep.
The correspondence in obtained this construction coincides with the RSK.
Yeah. Yes. What I've obtained here is RSK, and it's exactly the same thing. But, well, an advantage is that when you read a book about RSK correspondence, you have this tableau you obtain by inserting numbers one by one, and then you have the counting tableau, which is obtained like in a completely different way. And then there is a miracle that you can interchange them, and this corresponds to the inversion of a permutation. And here there's no miracle, because you transpose your array, it corresponds to the inversion of a permutation. And of course, what was downward operation becomes leftward, and vice versa. So in a sense, well, this explains some symmetries which were unexpected in which needed explanation in the standard setting. Well, it's not directly. Yeah, right. You're right. You need to transpose one of them, but yeah, it's still the same.
But now this way is considered more conceptual than the one.
Okay. And yeah, and for instance, if you consider an array which is a, well, this is what is called RS correspondence, right? Robinson-Shenstedt, and RSK is obtained if you take like arrays which are graphs, which have at most one, and which have exactly one entry in each column, and this will give you a bijection between these things and semi-standard times standard. Okay, and for instance, yeah, and well, one more thing is that this is of course related to Schur polynomials, and let me show you how. I'll consider a bidense array, and let me consider everything like this 2, 1. Right. Let me consider everything which is obtained by downward and upward operations from a bidense array. So here the arrows go in the opposite direction, so you can just inverse them and think that you're considering U1, U2, and so on. So in this picture, you have 8 arrays which are obtained from this fellow here, and the arrows, the operations D1 and D2, which bring these arrays one to another. And if I have an array, let me take its row weight. Questions? So let me count the number of balls in rows 1, 2, and 3. To such thing, let me assign a monomial in such a way. So this fellow will be x squared y, because there are 2 balls here and 1 here. This will be like xyz, and this will be xyz as well. And the last one, the top one, which I cannot reach, will be yz squared. So we have seen it somewhere at the beginning of the talk. So let me sum them up. And what I get is the Schur polynomial. And so the theorem is that Schur polynomial is obtained as the sum of monomials corresponding to the du orbit containing a bidense array. So another remark is that all the arrays in this setting are L dense, because this guy is bidense, D dense as well. And if you act by vertical operations on an L dense array, it remains L dense, right? So yeah, and L dense arrays, you can just also match them with something called Yamanouchi words, and this setting can provide a proof of the Littlewood-Richardson rule, a pretty easy one. I think the easiest proof I know. And also, if you just take the if you take all of the whole set of arrays, and if you take a bigrading with rows and columns, what you will get will be the Cauchy identity for Schubert. Okay, and these guys, well, I think the representation theory people have recognized the crystal operations on the crystal, the joint representation of SL3, right? So an 8-dimensional thing with 2 types of operations. Okay, so this will for me it's also a way to view crystals of GLN. Okay, so let me pass to the final part. These are what we call arrays with strings, and this is a way to view reverse plane partitions. Let me take the blocks of identical elements in columns, like 1, 1, 1 here. Take the corresponding balls and join them by a string. So here I have 2, 2. So this means that this 2 and this 2 is also joined. And now, well, I can say that if I view it as an array and I act by horizontal operations, of course this is not dense anymore. But if I introduce such elements as strings and I view them as something, as a whole thing, well, this thing becomes like D-dense. And then, well, we have introduced some combinatorial rules for dealing with such elements. And, well, there are some notions of horizontal operations and notion of matching where, well, I really don't want to get into combinatorial details here, but, well, there are these rules and which are dealing with a string as a whole thing. And sometimes you can move it, sometimes you cannot. And there are also yeah. So I this is more adapted to like French notation of okay, yeah. This can be misleading. Yeah, thank you. And we have also some new operations, new leftward operations like called break and fix, which break the matching and form a string, and which fix the matching by pulling this ball here. So okay, and well, here it requires some being quite precise about these operations. What you can do and what you cannot is not obvious. And but well, let me show you how these operations work. Matching between columns, like if you want to like move this ball left, you cannot because they're matched. Well, I'm saying I cannot do this, but I will. So I move this ball down, but instead I need to glue it together with this one. Oh no, this is like operation columns. This column and this column. The lows, yeah. This. Yeah, of course. There is such rule. I prefer to sweep the rug. Okay. So anyway, so yeah, let me show you how these operations work. Now there are some non-obvious situations like this one that somehow if you want to act by leftward operation on this guy, you need to cut this ball from this string and glue it to this guy here. So that's what you do. But at the end of the day, you get the bidense reverse plane partition array with strings. And you see that in this example, the number of arrays is equals to 7. And we actually had this example while we were decomposing the Grothendieck polynomial G221 into sum of Schur polynomials. Somehow this, well, all these arrays, they are the lowest elements in the arrays in the DU orbits obtained for Schur polynomials. Okay, and so we get so our result is, well, our main result is that we represent the monomials in the dual Grothendieck polynomials as sums over DUBF. DU stands for down and up, and BF for break and fix orbit of a bidense array. So we have something like this. We can act on it by break and fix, and also on each of these guys, we can act by usual upward and downward operations. And we sum up all the monomials, and we get the Grothendieck. Say again? Yes. Well, just a second. No. B and the F. Yeah, they compute with L and R. Yeah, they compute with L and R, but no, well, but actually the all the things here are like L dense, right? Yeah. So we do not know what a general L array is. We only know what is an L dense array. Oh no, that.
So it's really important which kind of operation.
Oh yeah. I think, no, yeah, I think you're right. Yeah, I think you're right. Okay, and the question is, well, do Grothendieck or just usual Grothendieck polynomials occur in representation theory? Do they have any, like, what are these? What crystals are these? Well, maybe there is in something in your p-adic business reminds you of. Okay, and this allows us to get a new proof of Lyman-Pilavsky and get another interpretation of these coefficients as Yamanouchi words. And well, here come some connections. People are doing something similar for set value Young tableaux into usual Grothendieck polynomials, and they have something called crystal operations with a K. A K stands for K theory, and there is a series of papers by Travis Scrimshaw with various sets of authors, and they define ad hoc crystal with a K operations on certain Young tableaux. For say, in one of the papers, they constructed it for rectangle Young tableaux, but they do not know what. Well, first, they do not know what it corresponds to geometrically or from the representation theory point of view, and then they do not know how to define it in general for a general Young diagram. They're not sure that it exists, and well, neither do we know what is, for instance, a general array with strings, and is it possible to fit these two pictures together because it would be nice to have them at once. Grothendieck and dual Grothendieck in the same picture with some sort of duality, like transposition of a matrix, bringing one to another. But this we don't know yet. And so the question is representation theory meaning of these guys, and is it possible to? Well, I think that no one really considered these coefficients or gave them any meaningful presentation, combinatorial presentation. They well, since these guys are positive, since these guys are Schur positive. No, I'm wrong. Yeah, that's not enough. Yeah, but no, I'm not sure. I don't know if this is known. Don't think so. Okay. And my big question is whether this rings some bell from the representation theory. Okay. Actually, that's all I wanted to say. Thank you.
Questions in addition to those one asked?
The geometric meaning. Yeah, that's right. They like K theory. Well, we would like to consider some like crystallization of K theory, but that's something I would expect. Just for Weizmann. Are they Grothendieck polynomials or well, they represent the ideal sheaves of Schubert varieties. Just times product. Yeah, but then you multiply two such things, you just construct a resolution. See positivity. Yeah. Not a covariance. Just all Grassmannian. Different Schubert varieties. Well, you take the ideal sheaves of Schubert varieties, and their classes in the K group. No, they are B. No, not G covariant because G is not the whole thing. Yeah, they're B.
Some tea outside.
Oh, great.
Next lecture in Ziskin 155.
Да.
Говоришь про эти самые графиники, думал, графиники.
Да.
Вот смотри, у тебя, значит,